So welcome. We are discussing few topics in engineering physics. Uh, we are going to start today quantum free electron theory. So in 1928, Sommerfeld has proposed this theory to explain the drawbacks of classical free electron theory, which was proposed by Drude and Lagrange in 1905. So the main uh, assumptions that they have taken in Drude-Lagrange theory was not able to explain why the trivalent atoms like aluminum shows less conductivity than the monovalent atoms like copper. So quantum free electron theory was able to explain few drawbacks of classical free electron theory. Here they consider that these electrons are not continuous energy, they have discrete energies. So the energy of this electron is taken as h cut square kappa square by 2m, and we know that this energy is kinetic energy, which is p square by 2m. So from this we can imply that momentum is h cut kappa. So when the electron is moving with this different energies, they have different velocities. So what we are going to take today is velocity frame, velocity, uh, what we say is Fermi velocities. So this Fermi velocity we are going to represent in the form of a sphere. So we'll take the velocity space Vx, Vy, Vz. Now there are different points in this sphere. These different points represents different velocities of electrons that is there in different states. Right. When electric field is zero, so the velocities are random and they cancel each other. So the net velocity is zero. But as soon as this we are taking some electric field here. Now we are applying electric field which is not equal to zero. So I am applying electric field, say this side is positive and this side is negative. So what happens, these electrons which is there will be moving this side. So we'll have a shift in this. So the electrons will move this side because negative charge repels. So the net velocity is there. There is change in the velocity delta V. So we are going to find what is the conductivity of these electrons. So for that we have to check what is the velocity. We know that momentum is mass into velocity. So mass into velocity is momentum, which is h cut kappa. So velocity is h cut kappa by m. And if you take change in the velocity delta v, which is h cut delta kappa by m star. So m star is effective mass of electrons, right? So this is what is delta v. Now we know that acceleration is rate of change of velocity. So we have h cut kappa d kappa by dt. So we have m. So we'll take later delta v, but now we are taking this velocity and differentiating with respect to time. Now when electric force is applied, we know that electric force is EE, and this is leading to acceleration in the system, the electrons. So these are called as drift velocities because applied electric field is drifting the charges. So this is drift velocity. Now from this we know A is equal to E by m. So both are accelerations. So we can substitute uh, this here. So we'll get an equation. So acceleration is dv by dt h cut by m d kappa by dt. So E is equal to, so you can substitute here. So E is equal to mass into A value is h cut kappa h cut by m d kappa by dt. So mm gets cancelled. So E is equal to h cut d kappa by dt. So we need d kappa, delta kappa. So d kappa is equal to E by h cut into dt. So I need the wave vector at time t equal to 0 to time t equal to t. So what I do is I do the integration of this. So integration of kappa of 0 to kappa of t d kappa is equal to E by h cut is a constant for a particular field. So we'll get t is equal to 0 to t is equal to t dt. So we know integration and differentiation gets cancelled out. So here we can write this as d kappa, that is kappa of t minus kappa of 0 is delta kappa E by h cut into t. We can say delta t. So this delta t is the time. So this delta t we are taking as relaxation time, tau. So relaxation time tau or tau f. So what is tau f? Tau f is, we know the distance by velocity. So here lambda f is mean free path and tau f is vf is Fermi velocity. So that's what we took initially, the Fermi velocity sphere. So vf. Now you can substitute there. So delta kappa is equal to E by h cut into lambda f by vf. Now you can substitute that here. So delta v is equal to h cut by m star E by h cut lambda f by v. Now what is current density? So we have the current density value. So the current density J is equal to number of electrons, charge of electron and the velocity. So this is the equation. We have one more equation for current density from Ohm's law, that is sigma into E. So both are J, so sigma E is equal to Ne delta V. Now substitute delta V from here. So h cut cancels, E is already there, so Ne square by m star, and this is nothing but tau f. So this you have E gets cancelled, so sigma, or you can write sigma E. So E gets, so what is the conductivity of these electrons is Ne square by m star into tau f. So this is your conductivity of electrons based on quantum free electron theory. So here the conductivity depends on number of electrons and the mean lifetime. Tau f is relaxation time or mean lifetime. So it defines that the time taken by the electrons before two collisions, and the mean free path is the average distance traveled by electrons before collisions. So this is the conductivity of the quantum free electron theory. So coming back to m star effective mass, why the uh, monovalent atoms shows more conductivity than trivalent or divalent atoms, which was not able to explain by classical free electron theory, is in quantum free electron theory this is important. So m star effective mass of electrons that is involved in the conduction process is important. So that's why in copper you can see more number of electrons participates in the conductivity process, so their conductivity is more. So what is this uh, effective mass equation? So if you take the equation of energy, so we have this energy from the Schrodinger's wave equation for this wave electrons. So that is energy is equal to h cut square kappa square by 2. So basically we are taking this equation. So if you differentiate this equation two times with respect to kappa, d by d kappa is equal to, so h cut by 2m, but here kappa differentiation is 2 kappa, so 2 gets cancelled kappa. Then again if you differentiate this with kappa, so you will get d square e by d kappa square is equal to h cut by m. So this we are taking as m star now, effective mass. So m star equation will be, one second, here this is square, excuse for that. So this is square, h cut square kappa square, then only it will be p square. So p is equal to h cut kappa. So h cut square, h cut square. So m star is equal to h cut square by d square e by d kappa square. So this is the effective mass equation. Basically, if you see this equation, so this equation represents a parabola. You can take this as y and this as some constant a, suppose say this is x square. So what is y is equal to x square is a parabola. So if you draw a graph between the energy versus, if you draw a graph between energy versus kappa, so this equation comes to be, so this traces a parabola and based on the effective mass. Suppose if effective mass is more, then you will have this parabola which is m2 star. Based on the effective mass of electrons, your EK diagram shows the different curvature. So overall, this is the quantum free electron theory explained by Sommerfeld, which is very useful to explain few things in uh, metals also, and it is very much useful to understand the drawbacks of classical free electron theory. And there are certain drawbacks in quantum free electron theory also. The quantum free electron theory was not able to explain what is the difference between semiconductors, conductors, and insulators. That we will be seeing in the next topics, that is band theory of solids. So thank you for watching. So I think it hopefully it will be very helpful for your preparation. Thank you.